this one, or these, I should say. For number one, we're asked to find angle A, this missing angle here. And of course, since this is a triangle, it just means all three of those angles have to add up to 180 degrees. So first thing we're going to do is we're going to add the 79 and the 38, which gives us 117 degrees. And we will subtract then to get 63 degrees. Angle A has to be 63 degrees. Now, questions 2, 3, and 4 go together. It asks, in this triangle, which side would be 4 inches? Well, that question doesn't make any sense unless we look at the next couple of questions as well. 3 is asking which side would be 8 inches, and 4 is which side would be 9 inches. This is saying, this is asking us to use the fact that the smallest side is opposite the smallest angle, and the largest side is opposite the largest angle. So of these three, 4 would be the smallest side, so it has to be opposite the smallest angle, the 38 degrees. That opposite side would be side AC. 9 would be the largest, so it has to be opposite the largest angle, so opposite the 79. That would be side AB. And the side that's left over for the 8-inch side, BC or CB, however you want to name it. Problem on the right here, a little hard to see once I drew in that angle bisector, but that is an equilateral triangle. And I drew in this angle bisector from vertex C to the opposite side. We know that if that's an angle bisector, it also is a median. In other words, it also cuts this other side in half. And it's also an altitude. In other words, it hits that opposite side at a right angle. Once we know that, angle CAB, that's this angle over here, well, we know that's 60 degrees because that's just one of the angles of that equilateral triangle, and we know that the angles of an equilateral triangle are always 60 degrees. ACD is right here. That is one of the angles that we bisected. That has to be half of the 60 degrees or 30 degrees. And angle CDB is right here. That is one of our right angles, so that is 90 degrees. One of the other things we worked on yesterday looked something like this. See if we could find that opposite side there. Oops. Let me label this correctly. This is 17.32 inches. What I actually want to find is we'll find y here if we draw this in. Well, being an isosceles triangle, an isosceles obtuse triangle in this case, we draw in that altitude at a right angle, we know that that cuts this in half. Half of 17.32 is 8.66 inches. So we've got 8.66 inches in each of those places. Now I can just look at this as just a single right triangle. And I'm going to redraw it a little bit like this. This is y, this is 10, not 10 inches. 10 inches would be up here now. This would be 8.66 inches. And to find y, it's simply Pythagorean theorem. Y squared plus 8.66 squared equals 10 squared. Now we can solve to find that y be 5 inches. There are a lot of neat things that we can do with these triangles if we know they're isosceles. We also learned that there's a lot of neat things just with a right triangle. if we know that's a right angle, let's say that we know that this is 6 inches, 8 inches, and 10 inches, which is a valid right triangle. If we draw the altitude from the right angle to the hypotenuse, so that's a right angle there where that hits the hypotenuse, it divides our triangle into two triangles that are both similar to the original large triangle. And we could go with pieces A, B, and C for that altitude, and we could find those missing sides. Now, it's a little tricky to see. Yesterday, I redrew the triangles off to the side for us. Today, we're going to try to pick them out. We're going to start by comparing to the little triangle here. That 6 in the big triangle would compare to the A. Because they're both the short leg. The 10 of the big triangle compares to the 6 of the little triangle because they're both the hypotenuse. If you're having trouble seeing that, like I said, just take this triangle, redraw it off to the side and label it. It might be easier to see which pieces go together. So we've got 6 times 6 divided by 10 tells us that A is 3.6. Now at this point we could find C by doing A squared plus B squared equals C squared. But I'm going to stick with, we've got the 10 from the big triangle equals, it corresponds to the 6 from that little triangle. C is the smaller leg, so that would be the 8 corresponds to C. The bigger leg, 8 corresponds to C. So we cross, multiply, and divide. 6 times 8 divided by 10 is 4.8 for C. And then we do the same thing for B. Looking at this triangle to find B, we know that the 10 is the hypotenuse of the big triangle, 8 is the hypotenuse of the little triangle. The 10 now corresponds to 8. E is the long leg, 8 is the long leg, so 8 corresponds to B. Cross, multiply, and divide. 8 times 8 divided by 10 gives us that B is 6.4. So we have found those missing pieces just by seeing or knowing that when we cut that right triangle with an altitude from the right angle, it gives us two small triangles that are similar to that original large triangle. Okay, so there is a quiz out there on this material. It's labeled quiz 47 and 48. It's labeled that way because it's on sections 47 and 48 out of the packets that you guys have been working in. Then we're going to switch gears and we're going to start talking about circles. There are a lot of pieces in circles, and in a couple hours of class, obviously at some point, maybe by the end of this week or early next week, we will see how the circles tie into the triangles. But understanding circles is vital, understanding how trig works, and it's actually where trig comes from. So we'll start out with the basics that we already know. If we have a circle, pretend that looks like a circle. From the center out to the edge is the defining characteristic of a circle. Actually, there's two defining characteristics. The first is the center, the location of the center. The second is that distance from the center out to the circle itself, which is called a radius. I'm going to throw in a lesser popular one here. A line segment that has its endpoints on the circle is called a chord. A special chord I'm sure how to draw this so that it'll special chord that contains the center of the circle is called the diameter. Now, as you can see here, that diameter is really just made up of 2 radii. So D is our abbreviation for diameter. R is our abbreviation for radius. The diameter is just equal to 2 times the radius. And the final feature that we'll talk about in this circle, before we draw another one for more features, is the distance around the outside, which of course is called the circumference. And of course, the formula for circumference, C, is what we use for circumference, capital C, is either pi times diameter, or, since 2 times the radius is the diameter, 2 times pi times the radius is for the circumference. And of course, remember the area of a circle is pi times the radius squared. That's all stuff we looked at last semester. But there are more features of a circle that we haven't necessarily talked about. One of those features is a line that's outside the circle that just touches the circle but never actually penetrates the circle itself, never goes into the circle. That is called a tangent line. If the line actually cuts through the circle, whether it starts in the circle and goes out, or if it starts outside the circle, goes completely through and out the other side, it is called a secant. Now, technical definitions, a tangent is a line that all of its points are outside of the circle except for exactly one point that is on the circle. That's that point of tangency. That one point where it touches the circle. All the other points are completely outside of the circle. A secant's technical definition is a line that contains some points inside the circle and some points outside the circle. Last semester, we talked briefly about something called a central angle.
Hey, is there such thing as a 45-degree radius? Asking for a friend.
A 45-degree radius? I would have to see the diagram or the setting that it was in. My guess would be if they're saying a 45-degree radius, they're asking for a 45-degree central angle and looking for either the arc of the circle or the area of the sector. But it would have to be a 45-degree central angle. This would have to be 45 degrees, and it would be looking for the features, like the length of this arc or the area that sector cuts out. But if you have a picture of that, bring it in, and I'll be happy to take a look at it and see if we can get a better interpretation for you. Well, that central angle cuts a portion of the circumference of that circle. That portion it cuts out is called an arc. And last semester we looked at arc length. That arc length, of course, is equal to the circumference of the circle times. That symbol there is theta. That would be this central angle here over 360. That's the fraction of the circle that arc is taking up. We also had, defining the area of this high wedge was called a sector. The sector area was defined to be the area of the whole circle, once again, times the central angle, theta, divided by 360. Again, that's a fraction of the whole area of the circle that sector takes up. And then, of course, the last thing we had that was kind of a pain to calculate, if I had a chord that connected 2 points on the circle, it actually cuts out a sliver of area on the outside edge of the circle here. That is called a segment. And we found the area of a segment. Unfortunately, the area of the segment didn't have a real simple formula. The segment area was equal to the sector area minus the area of the triangle. The triangle, of course, was this part of the sector in here that's left after you snip off that segment out there. Trig makes that calculation a lot easier, by the way. Well, as we're working on this, we have that central angle again. And let's just give this a size of 40 degrees. You can have an angle that has its vertex on the circle. The vertex being on the circle, having its vertex on the circle is called being inscribed. So that is called an inscribed angle. One of the relationships that we will use here is that the measure of the inscribed angle is half of the measure of the central angle, if they're on the same arc. You'll notice I drew these so both of those angles cut the same arc of the circle over here. So if that central angle is 40 degrees, this inscribed angle has to be 20 degrees. We will look at that rule more as we do more with our rules of circles. These two red lines here are both secants. They intersect out here to form an angle. That angle that is formed is simply called a secant angle. The size of that secant angle is also related to the arcs that it cuts. Now, there's two different arcs, so it's a combination of those arcs. And again, that's something we will look at over the next several classes, as to how do you use those arcs to determine that angle. And finally, we have an angle like this. This is, of course, a chord. This is a tangent. Because one side of that angle is a tangent, that is referred to as a tangent angle. The rules for the tangent angle are similar to the inscribed angle because it is still technically, the vertex is still technically on the circle, but it's not inscribed because both sides are not inside the angle. For it to be an inscribed angle, the vertex has to be on the circle, but both sides of that angle must also be inside the circle. The tangent angle has one side that everything but one point is outside of the circle. And like I said, there are mathematical relationships between these angles and the arcs they form on the circle that we'll be exploring over the next several classes. If I have a circle with a radius of 8 inches, another circle with a diameter of 16 inches. Well, we know that because the diameter equals 2 times the radius, that these circles have the same radius, the same diameter. As a circle only has 2 defining features, the location of its center and the size of its radius. I suppose you could say the size of the diameter, but that's just found from the radius. Any 2 circles that have the same radius or the same diameter are equivalent circles. The only thing that's different about them is the location of their center, which means that every other feature of them is equivalent. Talked about chords. If I have a chord here that is 10 inches long, it cuts an arc out here, this purple arc. Well, if within that same circle, I put in another chord that's 10 inches long, well, guess what? Those equal chords have to cut equal arcs. If I label this point A and B and C and D, arc AB has to equal arc CD, the same length. If I go over to my other circle over here, and I put in a chord that's 10 inches long, I'll call that arc EF. Because they have the same radius between the 2 circles, arc EF is also equal to AB, arc AB and arc CD. Let's say I put in a 70-degree central angle here. It is going to cut a certain arc out here. I'll call it GH. If I put a 70-degree angle in this same circle somewhere else, it would cut an arc again. Let's call that arc IJ. Similarly to what we had down here, arc GH is going to be equivalent to arc IJ. And of course, the next step would be to go over to this circle with the same radius. I put a 70-degree central angle in there. It cuts an arc. If I call that LK, arc LK is also equivalent to those 2 arcs because it has the circle has the same radius and we have the same central angle. This allows us to find missing features within a circle and from one circle to another. Over the next several classes, we're going to look at a lot of these types of relationships, relationships between the angles and the length of the arc, relationships between angles and other angles, and relationships between tangents, secants, chords, radius, and stuff like that that'll help us find missing features of a circle. The biggest thing that is confusing about these, as you can probably start to see right here, these circles fill up very quickly, and they have a lot of little features trying to separate them. One thing I would highly recommend is keeping extra paper and redrawing just the pieces of the problem that you need so that you can pick out the information that you need. For right now, because there's a quiz out there, I planned it a little short today. I'm still adjusting to not actually doing quizzes in class. In the packet that we worked out of yesterday, page 305, problems 1 through 8, I'm going to have you do all of those so you can identify the pieces and the names and stuff and the relationships that are given in those problems. So with that, we have about almost exactly 20 minutes left. If you'd like to get started on your homework, I will be on the network here to help you out.